Hello, so in this video we will talk about a concept called spanning trees, and then we will talk about an algorithm in which we can form those spanning trees using a graph. Okay, so let's start with the definition as usual. A spanning tree of a simple connected graph. This is important to know that it should be simple connected graph. Is a subgraph of G such that it is a tree and has every vertex of G. So a tree is what? Which has n vertices and n minus 1 edges, and it is connected. Okay, so there can be many spanning trees of a graph depending on the choice of our formation, but the number of edges in each choice must be the same. So whatever choice we use, we have to have the same number of edges for the tree, because the number of vertices are conserved. So this means the number of edges for a tree is always one less than the number of vertices. So that's why the number of edges should be conserved. Okay, and this has many applications in many areas like IP multicasting, and this is a more practical application. And in order to solve some problems, we can also have implementation of spanning trees in finding paths and circuits, or connected components. It should be connected components, and articulation points or cut vertices, and also can be used whether a graph is a bipartite or not, using spanning tree concept. Okay, now the question is that we can we can make a spanning tree by hand, but again, if we want a computer to solve it, then what should we should have a proper procedure. So one of those procedures is called depth first search. So for a depth first search, what we do is we start with an arbitrary vertex as a root. Remember, it's a spanning tree, so it has to have a root. Okay, when we say tree, we all assume that it's actually a rooted tree. Okay, and then we successively add vertices, edges and vertices starting from the from the root, such that each new edge is adjacent to the last vertex added to the path, and a vertex not already in the path. So I will keep on adding vertices unless I have already added a vertex which is adjacent to the vertex I am currently on. Okay, so then once we reach a stage where we cannot find any more vertices, then we move to the back. So we move next to the last vertex and see if we can add a path by finding vertices adjacent to that vertex. Okay, and no, not in the tree, of course. And this moving back, we continue this process until we have done we have covered all the vertices of the graph. Okay, and this moving back process is also called backtracking. Therefore, this depth first search is also known as the backtracking algorithm. So let's use this simple descriptive explanation of depth first search and try to find a spanning tree for this graph. So let's start with the root A. So now we know that A, B, C, and D are one path. So this is a possibility that we start with A, we go to B, we go to C, and we go to D. So this is my A, B, C, and D. Okay, now from D I don't have any other adjacent vertex which is already not in the tree, so I have to go back. I have to backtrack. I go back to C, and from C I can say F, E, and J. So I can say F, E, and J. Okay, so this is my F, this is my E, this is my J. So from J I have three options. I can go there, go there, go there. So let's say I choose to go there. So I can say G, H, I. So I can say G, H, I. So G here, H here, I here. But once I reach I, then the vertices are adjacent to I are H and J, which are already in the tree. So I have to go back, H, G, J, and then from J I can choose maybe this K. So I can say K, L, M, N, O. So this is K, L, M, N, O. Okay, and then again from O, I see that N is already in the tree and K is already in the tree. So I have to come back. I have to go at K again and J again. And then I have to choose another one. I have to choose P, Q, S, T, R. So I can say P, Q, S, T, and R. So this is P, Q, S, T, and R. So this is my spanning tree. Of this graph. Okay. Okay. So now a question comes: why is it called depth first search? Now note that whenever we have backtracked at O, we have backtracked at R, and we have backtracked at I. Okay, whenever we have backtracked, we go up on the level in a tree. Okay, so in other words, whichever, so for example, there was an edge in the graph B to F, but there is no edge from B to F here. Although B and F are connected, but no direct edge here. So every edge removed connects height wise or depth wise. Okay, so connects, when I say connects depth wise, it means that every edge which we have removed here, for example, we have removed, let's say another one, we have removed like K to N. Okay, this edge is no more there. So K and N are not on the same level. So K is an ancestor of N here. So every edge which is removed actually is connecting the ancestor. Okay, that's why, or it connects depth wise. Okay, or for example, there was an edge from H to J. So then you can say that H and J are at different levels, at different depths. Okay, so that's why it is a depth first kind of a approach here. Okay, now the question is that how can we find a pseudocode for this? Okay, so now for here we have to see, we have to read it again and see whether we can find anything which can be thought of as recursion. Okay, so let's say here, now what is a recursive nature? So process of carrying out the steps of adding edges and vertices starting from a vertex V and ending when we backtrack to V for the last time is termed as visiting. So for example, I chose this J here. Now I do this K, L, M, and O. Then I have to come back J to J. Then I do P, Q, S, R, T, come back to J. Then G, H, I, come back to J. Once I have done this whole procedure, starting from this J and coming back to J for the last time, this whole procedure means that I have visited or explored J. So, but the question is that if J is adjacent to K, for example, now K is added after J. So when do I explore K? K, L, M, and O, and then come back to K, and that's it. So this means the exploring of exploring of K should be done before the exploring of J. In other words, let's say J to G, G, J, G, H, I, and then exploring of G has to be completed before I complete the exploring or visiting of J. Okay, so then it means that I can say visit J, and then for each edge I add, I can say visit that vertex. Okay, so this is exactly what the pseudocode will be saying for the depth first search. Okay, so we have an input, a connected graph G with V and E, with V is equal to nodes V1 to Vn, and initialize T as the tree with only the root V1. So this is arbitrary here, and then we say visit V1, and in procedure visit we say our input is any vertex from the set of vertices, and we say for each W adjacent to V and not in T, we say add that W and edge VW to T, and we say visit W. So it will do recursively the same procedure which we have explained here from the node J, for example. So this is a very basic, you can easily program it based on your setting, based on your representation of the graph. We can easily come up with a code for depth first search. So now what is the complexity of that? Now complexity is we assume that adjacency list is available. So reading from that is taking zero computations, okay, or negligible computations. Okay. So then each edge is examined at most twice. One during its addition to the tree with a new vertex, and one possibly during backtracking. So for example, take the edge m to n. So from when we go from here, then when we were at m, then we checked what is the adjacent of m. We said n, okay. So we added this n. So this edge is now examined once. Now once we were going back from O to n, then we examined it again based on whether m is there or not. Okay, so then we go back. So similarly, you can see you can choose any arbitrary edge here, and you can see that each edge is actually done examined at most twice. Okay, some edges will not be examined because we don't have to backtrack them. Okay, so this means that the complexity is order of the number of edges here. And the number of edges is what? Number of edges in a simple graph is less than or equal to this. So this means this is a second order polynomial in n. So that's why we have the complexity O of n squared. Okay. Okay, so this is a brief introduction of depth first search and how we can use depth first search to actually form a spanning tree, and followed by some recursive representation of depth first search, so that we can actually program the pseudocode in a language. Okay, so this is it about this video. Hope it was easy to understand. Thanks for watching. Hope you liked the video.